So this is the section 6.2 question 91 vlog, and this subsection kind of focuses on where we left off in section 6.1, which was power series. In this section, we kind of go over the properties of power series, like how to build them, how to differentiate them, integrate them, combine them using algebraic formulas like multiplication, addition. It's just pretty much everything to do with power series, like what they are and how we can manipulate them to fit our needs. So the first thing is combining power series. Like if we have two power series where it's the first series is c sub n times x to the power of n, and then the second one is d sub n times x to the power of n, because remember, x to the power of n is the part of the power series that makes it the power series. So when we're separating the two inner classifications of the series, we do want to try to manipulate everything but the x to the power of n variable so that we can at least compare them on a similar basis. So say we do have those two power series and they converge onto the functions f of x and g of x. Well, respectively, the c of n times x to the power of n converges to f of x, and the d of n times x to the power of n converges to g of x. So if it's on a common interval, like if it's under the same interval, then we can say that we can combine the power series so that the series from n equals 0 to infinity equals the first power series, c sub n times x to the power of n, plus or minus d sub n times x to the power of n, and it also converges to f plus or minus g, which is the functions, like adding the functions together, they converge as well. So the next condition, or the next property, is that if m, say we have an integer m that is greater than or equal to 0, and any other real number that is b, the power series where b times x to the power of m times c sub n times x to the power of n converges on that first term, b times x to the power of m times f of x, which is the rest of the original power series. So if b is a real number and m is 0 or above, and that is being multiplied into the power series, when we find the convergence, we can just say that that component can be separated out from the actual series part of the equation and then multiplied that back into the convergence function, the f of x function. That way it will be a little bit simpler, like easier to simplify and find the convergence functions. And the final condition is same. It starts off the same as the condition, or sorry, property before this, where if there's an integer m that's greater than or equal to 0 and any real number b, if the series is where instead of cn directly times x to the power of n, if it's cn times bx to the power of m to the power of n, then that converges to f on f with b times x to the power of m inside for all x values in the interval. So I guess essentially what that means is if you have a constant, like a real number b that is being multiplied into your x variable, and you also have that x variable in your power series being raised by another real number above 0, then you can say that you can pretty much just conclude that the series converges on the function like from the x values, where the b times x to the power of m is the value, like the f of x value. So that should also be easier to help combine and find power series, like find the power series from find the converging function from the power series. So I guess moving forward, there is also multiplication of power series, which is just another algebraic operation that can be done on these series. Pretty much the multiplying power series just states that if they converge, if series A and series B, if they converge on a common interval, we can just multiply the series in this way, where it would be like it would be like the first element of the first series times the first element of the second series plus the first element of the first series times the second element of the first series. I don't think I'm explaining this well. So say we have a series Cn times x to the power of n, and we're multiplying that into the series Dn times x to the power of n. That results in a new series E sub n times x to the power of n. And how that works is it's when you're finding the values for this new series, it would just be C sub k times D sub n minus k, where k is your starting value and n is your ending value. So while you're going through the summation, if c is at 0, then, or if your starting value is k equals 0, then it would be c at 0 times d at your end minus 0. So your first value in your first series and your last value in your second series get multiplied together, and then that gets added up until you finally get to the multiplied product, like the final product of multiplying these two series. So again, the first series, as you're doing the summation, it increases through the list, and the second series, it decreases down the list. So it's matched on opposite ends of the series when you multiply the power series and add it together using the summation. This is another big concept, the differentiating and integrating power series. It is one of my harder concepts, and it did take me a little bit longer to kind of understand what it was saying in the first place. So typically, or I guess in layman's terms, what it's saying is, say we have power series A, which follows the same rules, the C of n times x to the power of n, and say that we are using the extended formula for this, the C sub n times x minus a over x minus a to the power of n, where a is the interval, or I'm sorry, I forgot the word. It's the axis that we're trying to rotate around, where usually it is just 0, so it would be x minus 0. But in this case, like, suppose that there might actually be an adjustment that needs to be made, and on the interval that actually does matter when you're trying to differentiate this and find the interval. So because we're using the longer formula, the interval a minus r, where r is the radius, and then comma a plus r, those coordinates for some value that of r that's greater than 0, we can, that is the interval that this power series converges on. Sorry, I'm jumbling up my words. But again, just to restate that, if you have your series in the form c sub n times x minus a to the power of n, a minus r comma a plus r is the interval that it converges on the power series. So it might be beneficial to leave it in that form if you get it that way, so you can immediately find the interval. And it is also differentiable on that interval, which is what the next part of this is. We can find f prime of the entire series by differentiating it term by term. So since there's several terms in this, the first thing that we will have to do is, well, I mean, we're differentiating it, so I'm assuming we can just move forward. Like the first one, like the first, the differentiated form of it would just be n times c sub n times x minus a to the power of n minus 1, because that's just how you take the derivative. And then from there, we can find, we can also integrate it again. Yeah, we can integrate it term by term again if we want to find the convergence interval one more time, like verify it. And if we want to integrate that f of x function, it would still converge on that same interval, a minus r, a plus r, but the integrated version of this would be c plus the series from n to infinity, c sub n times x minus a to the power of n plus 1 all over n plus 1. And I think this is just one of the quick forms, like the, I'm forgetting the word, but this is, I guess, the quick access for what would happen if you tried to integrate the f of x function that you found. So moving forward, I believe the last thing that's here is just I guess the last thing is two power series are equivalent if they're pretty much the same. Like if they have, if the x minus a to the power of n remains the same among the two series, and the c of n value and the d of n value also somehow like match up, like if there is a common ratio or something that allows the c of n times x minus a to the power of n to equal d of n times x minus a to the power of n, then we say that the two power series are identical. We say they are equivalent or unique. That is pretty much it in terms of concepts within 6.2. A majority of this actually is practice problems, and I had to learn a lot when going through these with the first set of practice problems. So I do still remember how to do some of it, but For this example, I'm going through question 91 in section 6.2. This question is the summation over the interval n equals 2 to infinity, n times n minus 1 all over 2 to the power of n, as f double prime of a half. Sorry, I said that so poorly. So we are evaluating the series on the interval 2 to infinity, and the series is n times n minus 1 over 2 to the power of n, and as f of double prime of a half. And then the original f of x function is actually f of x equals summation from 0 to infinity of x to the n. So we're given the original function, so I'm going to start there. F of x equals summation n equals 0 to infinity of x to the power of n. So we're trying to get to the double prime equation, I believe. So I'm actually going to take the derivative of this. So f prime of x equals the summation of n equals 0 to infinity, and then it's n times x n minus 1. So with this prime function, this is where I am right now. I'm trying to simplify this into a more workable form for a second integration or for a plugin. So I'm gonna try to see what the values look like and then derive a simpler form from there. At x equals 0, or at n equals 0, it equals 0. At n equals 1, it equals 1x to the 0. At 2, it equals 2x to the first, 3x to the second. So n plus 1 times x to the n minus 1. So I'm actually going to rewrite this as the summation of n to infinity as n plus 1 times x to the power of n, because I believe this is going to make it a little bit easier to factor again. And actually, I think we can separate this even further, because according to this property of adding power series, since the x plus n is being distributed to both of these, we can say the summation of n starting at 0 to infinity equals x times n plus the summation of n going to infinity of n times x to the power of n. So since it was n plus 1 times x to the power of n, I just split that one power series into two, where the series within the summations are x to the power of n and then n times x to the power of n. This way I can pretty easily I believe get to that second derivative where I can plug in the half. So x to the power of n is just equal to, the integral of that is just equal to n x to the n plus n squared times. So I apologize for that. I realized that I was looking at 93 while evaluating 91. So everything after the concept I'm just going to go over right now. I'm sorry about that. That was just, I'm just extremely tired, and it was just a bonehead mistake. But back to where we were, the original function that they gave us to evaluate is n over 2 to the power of n, and they give us f prime at a half. They're asking us to evaluate at f prime at a half, and then they give us that f of x equals the summation of the series x to the power of n. So the first thing you do, start with the series that they give you, the original f of x equals summation of x to the power of n. From there, we can immediately differentiate, take the first derivative, and that gives us that n times x to the power of n minus 1. And then from there, again, I think I was just mixing up my words. It's the n plus 1 times x to the power of n, like if you rewrite it that way, you can split that up into two terms, the x to the power of n, the summation of x to the power of n, and then the summation of n times x to the power of n. So since this is the new, since this is the differentiated form, the f prime function, now we can actually plug in the 1/2 into the f prime function. So n. So right now where I am is I plugged in 12 to the f prime function and I got f prime of 12 equals the summation of n times a half to the power of n plus a half to the power of n. So I just reviewed one of the simpler questions because I kind of got lost on what to do after I plugged in the f prime at 12. And I think what I need to do now is I can use the closed form function of the x to the power of n because that x to the power of n summation it is directly equal to 1 over 1 minus x. So then what we can do is we can set the summation of x to the power of n equal to f of x, which equals 1 over 1 minus x. And this is one of the closed forms that are provided. And we also have it provided that f prime of this function equals -1 times -1 over 1 minus x squared. So how that would just be 1 over 1 minus x squared. And then now we can plug in the half. So f prime at 12 equals 1 over 1 minus 1 half. Or, yeah, 1 minus 1 half. Squared. Yes. Yes. And then if we evaluate that, that's 1 1 oh, that's just 1 over 1/4, which equals 4. Yeah, just 4. So f prime at 1/2 equals 4. And then what we can do now is we need to evaluate the original function. Since we now have what f prime at 1/2 equals, we can set up where the summation of n to infinity of the original function n over 2 to the power of n equals trying to figure out what to set this equal to so I can simplify down. So I'm currently at f prime of 1/2 equals 4, and the next step I thought I would write down the original series and set it equal to the derivative series that we just found at 1/2, which is just 4 minus or plus. I don't know what to add or subtract it by. So I think I realized my mistake. When we were first getting the derivative function and when I first plugged in that x equals a half, I forgot to extend that summation to both the terms where the integrated f prime of one function, f prime of a half function equals the summation of n times x to the power of n plus another summation of x to the power of n. So it should read f primed of a half equals summation of n times half to the power of n plus the summation of half to the power of n. So now, since we have this function where it's n over 2 to the power of n, that is part of that equation that I just read out. So I'm going to label it to see it better. I think I fixed my own problem, but I'm not sure. It works out, I think, but in my work, what happened or what I did was after I found the first equation that we got, after we got the second derivative function or the first derivative function, this is the equation we got with the half inside of it, and I set that equal to equation 1. Now what we're doing is we're trying to rewrite or solve for the original equation, and since now we know f prime at a half, we can solve for the original that it's asking for, which is the summation of n over 2 n 2 raised to the power of n. So now what we can do is we say that summation of n over 2 to the power of n equals 4 minus half to the power of n. And I believe there's a closed form or something for that. So I can set that equal to actually the summation of n over 2 to the power of n equals 4 minus a over 1 minus r. Yes, because that is I think that's also the closed form of this half to the power of n, or I don't know why I did that, but I think Actually, yeah, that is the right formula. So it equals to a over 1 minus r because a is 1 in this situation, and we just figured out that r is a half since that's what we're evaluating on. So it would be 4 minus 1 over 1 minus a half. So that would equal 4 minus 1 over a half, which would equal 4 minus 2, which would equal 2, which I think that's the answer. I'm not sure if I was completely off, but I used the system of equations, as well as I used the original equation that we stemmed this off of, the C of n times x minus a to the power of n. I believe that's it for section 6.2. There isn't anything more we can do. We found the value of f prime at a half, and we found we evaluated the original function with the value, and we found that it is equal to 2. So that is the end of 6.2. If there is anything I can clarify or clear up, just let me know. Again, the primary motive of this entire section is understanding power sets, experimenting with them, doing arithmetic with power sets like multiplication, addition, and also one of the bigger things is learning what the power series representation is of like using the power series representation, actually, like x to the power of n equals 1 over 1 minus x, if f of x equals 1 over 1 minus x, then the series equals, as n equals 0 and goes to infinity, x to the power of n. And along with that, knowing like what the derivative of said function is too, which we use to 1 over 1 minus x squared. Along with that, there is pretty much just practice, just understanding how everything gets put together, and using the system of equations that you build on your own to solve for whatever it asks you within the specific question. It might give you the original function and a value at a random third derivative of that function, and then ask you to evaluate. It might just ask you to might just ask you to integrate the given series term by term from 0 to whatever, and then expand that into an indefinite integral. Like, there are different components that can be given, and you can either work forwards or backwards depending on which equation you need to arrive at to be able to plug in either the derivative function or the integral function and then solve for whatever they ask you to solve. But that is essentially what 6.2 is mostly about. Thank you.